Partial derivatives. Functions of two or more variables require partial derivatives. Here we'll look at the case where the domain has two variables. So if f is a function of two variables, its partial derivatives are the functions that we call fx and fy, and they are defined in the following way. Fx, which is the partial derivative with respect to x, is the limit as h goes to 0 of f of x plus h y minus f of x y, all divided by h. So what you can see is the variable x is changing, but the variable y is held constant. When we take the derivative with respect to y, we do the opposite. We hold the variable x constant, and now y is allowed to change. There are several notations for partial derivatives. So if z is equal to a function of x and y, we can write the partial derivatives as we see above here. So that is fx of xy, or simply fx for short. We can write partial derivative of f with respect to x. And if you do some research here, you'll find different ways that people will say this. We really shouldn't say df dx, even though this partial derivative symbol sort of resembles the letter D. It's not really the letter D. So although there are multiple ways of saying this, the way I will say it in this class is partial f, partial x. I find that it rolls off the tongue a little bit better saying it that way. This is also the same notation. This is the partial derivative with respect to x of the function xy. We can also write partial z, partial x, because z is the function f. And furthermore, we can even write f1. Now what this is here is the derivative of f with respect to the first variable. This is also a similar notation, and so is this. Now the notations that I'll be using primarily in this class is the fx notation, the partial f, partial x notation, and occasionally also partial z, partial x. And of course, the same thing is true for the partial derivative with respect to y. So all of these notations here are similar to the ones up here. The only difference is now we're differentiating with respect to y. Now, in terms of finding partial derivatives, the basic rule for doing this is when you're taking the partial derivative of a function with respect to the variable x, you just think of the variable y as a constant. So you just treat it like a number, and you take a normal derivative like you would with respect to x. And when taking the partial derivative with respect to y, now you simply regard x as a constant, and you differentiate the function f with respect to y. Let's take a look at an example. So here we have the function f of xy equals x cubed plus x squared y cubed minus 2y squared. And we're being asked to find the partial derivative with respect to x, and then evaluating it at the point 2, 1, and then also finding the partial derivative with respect to y and evaluating it at the point 2, 1. So first, let's find fx of xy. So this is the partial derivative with respect to x. So the way we do this is pretty simple. We're going to differentiate term by term. When I see the variable x, I just take a normal derivative. So the derivative of x cubed with respect to x is 3x squared. Plus. Now here, notice that we have x squared times y cubed. But because we're taking the derivative with respect to x, we're going to treat y cubed as though it were a number. So we're basically just taking the derivative of x squared, which is 2x, and then simply multiplying by y cubed because, again, it is regarded as a constant. Now finally, this last term here, we have negative 2y squared. the derivative of 2y squared with respect to x is 0. So the partial derivative with respect to x is 3x squared plus 2xy cubed. Now, to find the partial derivative with respect to x at the point 2, 1, we simply plug in x equals 2 and y equals 1 into our partial derivative. So this will be 3 times 2 squared plus 2 times 2 times 1 cubed, right? So again, x equals 2 and y equals 1. Now if we do the math on that, we get 3 times 4 is 12, plus 4 is 16. Now taking the partial derivative of the partial derivative with respect to y, we basically do the same thing, but now we are going to treat x as a constant. So the derivative of x cubed is 0. For the next term, x squared now is regarded as a constant, and the derivative of y cubed is 3y squared. So we have x squared times 3y squared. Finally, minus the derivative of 2y squared is 4y. So I recommend cleaning this up a little bit. So instead of writing x squared times 3y squared, let's write 3x squared y squared. And now when I want to plug in the point 2, 1 into this partial derivative, I simply let x equal 2 and y equal 1. And we get 3 times 2 squared times 1 squared minus 4 times 1. And this is 3 times 4 is 12, take away 4 is 8. And finally, let's keep in mind that I could have used different notation. I could have said the partial derivative of f with respect to x is equal to 3x squared plus 2xy cubed. And the partial derivative of f with respect to y is equal to 3x squared y squared minus 4y. So this is alternative notation. Now I chose to use this notation because that is the notation that they gave when they asked for the partial derivatives, but this is the same thing. Now in terms of the last part of this, if I were using this notation, what I would write is the partial derivative of f with respect to x evaluated at the point 2, 1 is equal to 16, and the partial derivative of f with respect to y evaluated at the point 2, 1 is equal to 8. So you will find, I think, that this notation is a little bit more convenient than this notation, but truth be told, we should be familiar with all the different types of notations that we might see. Next example, f of x here is sine of x divided by 1 plus y, and we want to find, again, both partial derivatives. So the partial derivative of f with respect to x, what you do is you just regard y as a constant and x as the variable, and just ask yourself, how would you take the derivative of sine of some variable function? Well, we know it would be cosine of that function. And then the chain rule says you have to multiply by the derivative of the inside of that function. Now again, since we're taking the derivative with respect to x, 1 plus y is a constant. And so you can think of x over 1 plus y as 1 over 1 plus y times x. So what we have is a constant, essentially, multiplied by x. And the derivative of a constant multiplied by x is the constant. So we're simply going to multiply by 1 over 1 plus y. Now, in the end, I recommend not leaving this here. It's better if we put the 1 over 1 plus y in the front, and then cosine of x over 1 plus y. Now, of course, alternatively, you could write the cosine of x over 1 plus y divided by 1 plus y. I do think that this notation is best. Now the partial derivative with respect to y. Same idea. The derivative of sine of anything is cosine of that thing. So cosine of x over 1 plus y. And then we're going to multiply by the derivative of this thing, but now that derivative is with respect to y. So now, when you have x over 1 plus y, let's think of that as x times 1 plus y to the negative 1. Now, when I take the derivative of that, x is a constant, and the derivative of this part will be negative 1 times 1 plus y to the negative 2 times the derivative of the inside, and the derivative of y with respect to y is 1. So the derivative there ends up being negative x over 1 plus y to the second power. And again, I would move this in front of the cosine function. And there is our derivative. Now let's just take a quick look at the graphical meaning of partial derivatives. So if you have a function z equals f of xy, you are going to get some surface in 3 dimensions. If you pick a point on that surface and you find the derivative at that point, what you are essentially doing when you find the partial derivative with respect to x is you're finding the slope of the tangent line that is parallel to the x-axis. And when you take the partial derivative with respect to y, you are finding the slope of the tangent line that is parallel to the y-axis. And this is because when you take the partial derivatives with respect to one variable, you are holding the other variable constant. Now, if you think about it, when you have a point on a surface, you can draw infinitely many tangent lines through that point. But the partial derivative is only going to focus on the tangent line parallel to the x-axis and the tangent line parallel to the y-axis. So for this next example, we're going to compute the partial derivatives and evaluate it at the point 1, 1. And then we're going to interpret these values as slopes. So first of all, let's find the partial derivative with respect to x. So I'll just write fx here. The derivative of 4 is 0. The derivative of negative x squared with respect to x is negative 2x. And the derivative of negative 2y squared with respect to x is 0. The partial derivative with respect to y, well, the derivative of 4 is 0. The derivative of negative x squared is 0. And the derivative of negative 2y squared is negative 4y. So now, if I want to evaluate these derivatives at the point 1, 1, I can write the partial derivative with respect to x evaluated at 1, 1 is going to be this derivative with x equals 1 and y equals 1. Now, of course, there is no y value here, so we will only be plugging in x equals 1. And that is negative 2 times 1, which is negative 2. And the partial derivative with respect to y evaluated at 1, 1 will be negative 4 times 1, which is negative 4. Now, the interpretation of these slopes on the graph, here you can see we have a graph of the surface, which is this paraboloid. And when we're looking at the partial derivative with respect to x, what we're doing is we're taking a vertical plane and we're intersecting this curve at the point 1, 1, 1, right? So in case you're wondering why it's 1, 1, 1, when x is 1 and y is 1, if you plug those in, you also get z equals 1. So the point of tangency here is the point 1, 1, 1. If we find a vertical plane that intersects that point and is parallel to the x-axis, the slope of the tangent line there on that plane is equal to negative 2. That's what the partial derivative with respect to x is measuring. The partial derivative with respect to y, we just do the opposite. We take the same surface here. We take a plane parallel to the y-axis at the point, and the slope of that tangent line is -4. That's the graphical interpretation of slopes of tangent lines using partial derivatives. In the next problem, if we define the body mass index of a person as a function of two variables, so B stands for body mass index, of a person with mass M and height h, what we want to do is calculate the partial derivatives of B for a young man with a mass of 64 kilograms and a height of 1.68 meters. And then we want to talk about what those partial derivatives mean. So let's go ahead and find the partial derivative of B with respect to M, the mass. So to do this, let's remind ourselves that M divided by h squared is the same as 1 over h squared times M. So with respect to M, 1 over h squared is a constant. And of course, the derivative of M with respect to M is 1. So we just get 1 over h squared. The partial derivative of B with respect to h. Now let's write this a little bit differently. Let me write it as M times h to the -2. With respect to h, M now is a constant. And then we'll take the derivative of h to the -2, which is -2h to the -3. And this can be simplified as -2m divided by h cubed. Now let's talk about the meaning of what is the partial derivative of b with respect to m evaluated for a young man with a mass of 64 kilograms and a height of 1.68 meters. So to do this, we have to plug in m equals 64 and h equals 1.68 into our partial derivative. Now, of course, our partial derivative in this case only has one variable, h, so we will only be plugging in 1.68 there. So we get 1 divided by 1.68 squared. And if you do the calculation on this, you get approximately 0.35. And this is kilograms per square meter per kilogram. So what does that mean exactly? Well, since this is the partial derivative with respect to mass, we are holding the height constant. So if we assume somebody's height does not change, then the change in their BMI for every kilogram that changes is approximately 0.35. So what that means is that if you keep the height the same, every kilogram of weight gained is going to increase the body mass index by 0.35. And also, every kilogram of mass lost would reduce the body mass index by 0.35. It's similar for the other one. So if I take the partial derivative of b with respect to h, and I evaluate it at 64 and 1.68, now we're going to plug in m equals 64 and h equals 1.68, and that is 1.68 to the third power. And if we do the math on this, we get approximately -27, and this is kilograms per meter squared per meter. Now, what does this mean? Well, this means if we hold the mass constant, so if the weight or mass of a person does not change, for every change in the height, for every 1 meter change in the height, the body mass index is going to be reduced by 27 points. Now, of course, it's very unlikely that someone would grow by 1 meter, because 1 meter is a lot for somebody to grow by. but it gives you an idea that as somebody gets taller, their body mass index comes down. So this is a good way to evaluate how does the body mass index change when we change one variable but we hold the other variable constant. In the next example, we're going to talk about implicit differentiation. Here we want to find the partial derivative of z with respect to x and the partial derivative of z with respect to y. And z in this case is a function of x and y, but it is implicitly defined, meaning that the z is mixed in with the x's and y's in the equation. So the way we do this is we simply take our equation, x cubed plus y cubed plus z cubed plus 6xyz plus 4 equals 0, and we're going to take the partial derivative of this with respect to x, and we're going to take the partial derivative of the other side with respect to x. So anytime you see an x, you're going to take a regular derivative. You're going to think of y as a constant. And then anytime you're going to see a z, you're going to think of that as a function of x. So the way to think about this is when you're looking at partial z, partial x, you're going to treat z and x as variables, and you're going to think of y as a constant. So let's do this. The derivative of x cubed with respect to x is 3x squared, plus the derivative of y cubed with respect to x is 0. Now this next part is a little bit trickier. The derivative of z cubed with respect to x is 3z squared, but then we have to multiply by the partial derivative of z with respect to x. This is the chain rule, and you do this when you take implicit derivatives in single variable calculus. Okay, next up we have plus. Now we're looking at a product. We have 6x multiplied by yz. So I have to use the product rule here. Product rule says I take the first function, which is 6x, and I'm going to multiply that by the derivative of yz. Now y is a constant, and the derivative of z is partial z partial x. Plus, now I'm going to take the second function, which is yz, and I'm going to multiply it by the derivative of 6x. The derivative of 6x with respect to x is 6. Plus, derivative of 4 is 0. And the derivative of 0 on the other side is 0. Now let's clean it up. We have 3x squared plus 3z squared times partial z partial x plus 6xy partial z partial x plus 6yz is equal to 0. And now we're just going to algebraically solve for partial z partial x. So I'm going to factor partial z partial x out of those two terms. And the other two terms here and here, I'm going to subtract those over to the right-hand side. And finally, I'll divide to solve for partial z partial x. So partial z partial x equals negative 3x squared minus 6yz, all divided by 3z squared plus 6xy. And I should make a note that this answer can actually be simplified because you'll notice all these numbers here are multiples of 3. So if we factor out and cancel that common factor of 3, the numerator is going to become negative x squared minus 2yz, and the denominator becomes z squared plus 2xy. And this is the simplified version of that partial derivative. Now, for the last part of this, it does say to evaluate these partial derivatives at the point -1, 1, 2. So let's go ahead and take care of that. So the partial derivative of z with respect to x, evaluated at the point -1, 1, 2, is -1 squared minus 2 times 1 times 2 divided by 2 squared plus 2 times -1 times 1, Be really careful when you're doing this. We have lots of variables and it's really easy to make little mistakes. But this is going to end up being -1 minus 4 divided by 4 minus 2. And this is -5 over 2. Now let's take the partial derivative of z with respect to y. So to do this, once again, we're going to take the entire equation and we're going to take the partial derivative with respect to y of both sides. Let's go ahead and go through it. The partial derivative with respect to y of x cubed is 0. Partial derivative of y cubed with respect to y is 3y squared. Derivative of z cubed with respect to y. Now remember, z is a function of y now because we're taking the derivative with respect to y. So this is going to be 3z squared times partial z partial y plus, here we do the same thing as before. So for this one, I'm going to think of 6xy as being one function and z as being the other function, and we're going to use the product rule. Product rule says we take the first function, 6xy, multiply it by the derivative of z. We're taking the derivative of z with respect to y, so that is partial z, partial y. Plus, then we take z and we multiply it by the derivative of 6xy with respect to y. 6x is a constant, so the derivative of 6x times y with respect to y is 6x. So we get 6x times z. Derivative of 4 is 0, and the derivative of 0 is 0. So again, simplify. We have 3y squared plus 3z squared, partial z, partial y, plus 6xy, partial z, partial y, plus 6xz is equal to 0. And then we're going to factor out partial z, partial y out of these two terms. We're going to move these terms here to the other side. So this is very similar to the work that we did just a few minutes ago. And then when you factor out the partial derivative there and divide by what's left over, we have 3z squared plus 6xy. And finally, canceling a 3, we end up with -y squared minus 2xz divided by z squared plus 2xy. All right. Now, the partial derivative of z with respect to y, evaluated at the point -1, 1, 2, is -1 squared minus 2 times -1 times 2 divided by 2 squared plus 2 times -1 times 1. And this is -1 plus 4 divided by 4 minus 2. And this is 3/2. So here's the partial derivative. And here is the partial derivative evaluated at the point. In our next example, we have a function f of 3 variables, x, y, and z. And it is e to the x times y times the natural log of z. So here we can talk about the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. So we just have more variables, but it's the same concept. So when I take the derivative with respect to x, I treat x as a variable, everything else is a constant. So natural log of z is a constant, and it's being multiplied to e to the xy. The derivative of e to the xy is e to the xy multiplied by the derivative of xy with respect to x. And then, of course, multiplied by the natural log of z, because again, this is a constant, so it just comes down. What is the derivative of xy with respect to x? Again, y is a constant. So the derivative of a constant times x is that constant. So this is just going to be y e to the xy times the natural log of z. So if you're wondering, this came from here. All right, next up, what is the partial derivative with respect to y? It's very similar. The derivative of e to the xy is e to the xy. Then we're going to multiply by the derivative of xy, but this time with respect to y. And then times the natural log of z, because again, natural log of z is a constant. The derivative of xy with respect to y is just x. So this becomes x e to the xy times the natural log of z. And finally, what is the derivative with respect to z? Well, now, e to the xy is a constant, and we only need to multiply by the derivative of the natural log of z. So this is going to be e to the xy multiplied by derivative of natural log of anything is 1 over that thing. And then, of course, times the derivative of that thing. But the derivative of z with respect to z is 1. So this is simply e to the xy over z. So those are our 3 partial derivatives for this multivariable function. We can also talk about higher derivatives, specifically second partial derivatives of a function. So to understand this, suppose we have some function f which has independent variables x and y. If I have the first partial derivative with respect to x, and I take the derivative of that with respect to x, we call this derivative fxx. And just for clarity, the first x tells you what you took the derivative to with respect to the first time, and the second x tells you what you took the derivative with respect to the second time. But if I have the function fx, I could have chosen to take the derivative of that function with respect to y. We would call this second partial derivative fxy. Likewise, if I took the first derivative of it with respect to y, I can take the second derivative with respect to x. We call this derivative fyx. And finally, if I have the derivative with respect to y, I can take the derivative of it with respect to y, and its notation is fyy. Now, there is alternative notation, as you can see here. I don't really use this notation. We won't really be using this notation in my class. But if you have the partial derivative with respect to x and you take the derivative of that with respect to x, you can use the typical derivative notation partial squared f partial x squared. Likewise, if you have the derivative with respect to x and then you take the derivative with respect to y, in this notation we would write it like this. Here is the derivative with respect to x, and now we're taking the derivative with respect to y, and this gets written in this way. Now I want to point out that when you use this notation, the x is the first derivative that you take, and the y is the second derivative that you take. In this notation, it's backwards. This one is the first derivative that you take, and this one is the second derivative that you take. So you have to be very careful not to get those confused. Now, again, this is just yet another reason why I really just prefer to use this notation. I feel like this notation is much more straightforward. So let's go ahead and take a look at a couple of examples. Here we want to find all the second partial derivatives of the following function. So to do this, what we need to do first is find the first partial derivatives. So the derivative with respect to x here is going to be 3x squared, and then here we're going to treat y as a constant, so it's going to be 2x times y cubed, and then again this y is a constant which goes away. And the derivative with respect to y, this is going to be a constant now, so that's going to go away. And now in the second term, x squared is a constant, so the derivative here is 3y squared times x squared. And finally this. Now as a note, these are the same partial derivatives that we took just a minute ago. But now let's talk about the second partial derivatives. So if I take the derivative with respect to x here, and I take the derivative with respect to x again, I'm simply going to take the derivative of this with respect to x. So that's going to give us 6x plus, and again, since it's with respect to x, y is a constant. The derivative of 2x is 2, so it's just going to be 2y cubed. Now, if I had done the derivative of x and then y, all I would do now is take the derivative of this with respect to y. If I do that, the derivative of 3x squared is going to be 0. And with respect to y, 2x is a constant, so the derivative becomes 2x times 3y squared, which is 6xy squared. Now we can do the same thing over here. If I start with the partial derivative with respect to y, I can take the second derivative, also with respect to y. We would call this fyy. And that is going to be 3x squared times 2y minus 4, which is 6x squared y minus 4. But I also could have taken that derivative and then taken the derivative with respect to x. The derivative here with respect to x is going to be 3 times 2x times y squared. And now the derivative of 4y with respect to x is 0. And so this derivative is 6xy squared. So here are the 4 second partial derivatives for that function. Now I would like to point out that the mixed partial derivatives, these are called the mixed partial derivatives because they mix the two variables xy and yx. Notice that the answers for those are the same. Now, is this a coincidence? No, of course it isn't. So we have a theorem here called Clairaut's theorem. It says suppose f is defined on a disk that contains the point AB. If the functions fxy and fyx are both continuous, then they are both equal. So the mixed partial derivatives are always equal to each other unless for some reason you're dealing with a discontinuous function. Now this next example is just for fun. Here we have a function of 3 variables. So f of x, y, z is the sine of 3x plus y times z. And I want to find f, x, x, y, z. Okay. What we do is we just focus on the first one first. So we're going to take the derivative with respect to x. The derivative of sine of anything is cosine of that thing. And then we are going to multiply by the derivative of that thing with respect to x. And this is going to give us the cosine of 3x plus yz multiplied by, what is the derivative with respect to x? Well, the derivative of 3x with respect to x is 3. And the derivative of y times z with respect to x is 0. So fx is 3 cosine of 3x plus yz. Now we need to do the derivative of that with respect to x again. So this will be fxx. 3 is a constant. What is the derivative of cosine of anything? Well, we know it is negative sine of that same thing. And then we have to multiply by the derivative of that thing with respect to x again. This is going to be negative 3 sine of 3x plus yz multiplied by, what's the derivative of this with respect to x? Well, again, it's 3. So our answer here is negative 9 sine of 3x plus yz. Next, we are going to take the derivative of that function with respect to y. So this is going to be fxxy. Negative 9 is a constant. The derivative of sine of anything is cosine of that thing. So we have negative 9 cosine of 3x plus yz multiplied by the derivative of 3x plus yz, but this time it's with respect to y because that's the derivative we're taking. So this is going to be negative 9 cosine of 3x plus yz multiplied by, what is the derivative with respect to y of 3x? It's 0. What's the derivative of yz with respect to y? It's z. So this is equal to negative 9z cosine of 3x plus yz. And finally, our last derivative is with respect to z. So we are going to go to this one now and take its derivative with respect to z. Now here, this is a little bit more complicated because you can see we have a function of z here and we also have a z in here. So we have a product of two functions. So to do this derivative, we are going to take the first function, negative 9z, and multiply by the derivative with respect to z of cosine of 3x plus yz. Plus, then we take the derivative of negative 9z, and we're going to multiply that by cosine of 3x plus yz. So this is negative 9z. Derivative of cosine of anything is negative sine of that thing, multiplied by the derivative of this thing with respect to z. That is going to be y. Plus the derivative of negative 9z with respect to z is negative 9, and then cosine 3x plus yz. And now we just clean it up. We have a negative and a negative, that's a positive. 9 times y times z. Sine of 3x plus yz minus 9 cosine of 3x plus yz. And this is our fourth partial derivative, but it's with respect to x, with respect to x, with respect to y, and then with respect to z. And that concludes this video lesson.